Welcome back to my YouTube channel, guys. I'm Dr. Shah Fahad Khan, and we are going to do lesson 3 of atomic structure. This lesson will just simply tell you and explain qualitatively the variations in atomic radius and ionic radius across the period and down the group of a periodic table. So let's get started with it now. This is the general trend, and this is the statement part. Going down the group, if you look at the size of of the atoms, the size of the atoms is actually increasing, which actually means going down the group, the atomic radius increases. Going across the period, if you look at this period, it's very obvious over here as well that the size of the atomic radius is actually shrinking. So across the period, it decreases, and down the period, it increases. All right, so you need to know these two trends. We've just stated them. All right, this is an exam question to state the trend. The next exam question is to explain each of these trends. So let's first explain the group trend, then we are going to explain the period trend. Before explaining these two trends, there's a concept that you need to know, and this concept is called the shielding effect. Now, what is shielding effect? Let's just read through the paragraph first, and then I'm going to explain it. It is the protection that the inner shell electrons would provide to the outer shell electrons against nuclear attraction. It depends upon the number of complete inner shells. Since the number of shells increase down the group, the atomic radius would increase. Now, let me explain all of this. Just look at this diagram, and this would explain shielding effect to you. You've got a centrally placed nucleus that is positively charged and is constantly exerting an attractive force on all of these electrons. You've got electrons here as well, and you've got electron over here as well. This is the outer electron, and these are the inner shell electrons. This is also an outer electron, right? The nucleus will try to pull it inwards. It will try to pull it inwards, right? This is the nuclear attraction that is exerted on the outer electron. But what would these electrons do? Are they also negatively charged? Yes, they are. If they are negatively charged, and this is also negatively charged electron, the inner electrons would actually exert an opposing effect on this outer electron. The inner electrons would actually repel the outer electron because these are like charges. And you know that like charges always repel each other. Like charges repel. So, this repulsive force that the inner electrons exert on this outer electron is actually the shielding effect. Okay, and because it's actually weakening the effect of attraction to some extent, therefore it's called the shielding effect. Okay, it's protecting or shielding the outer electron from the attraction of the nucleus. I hope that makes sense. If it doesn't, you can ask it in the comment section, by the way. All right, then the next thing is, if this is the nuclear attraction, this is the shielding effect, what does it depend upon? It actually depends upon how many electrons you have, not basically electrons, it depends upon how many complete shells you have inside. All right. So if you have an atom with, let's say, four shells on the inside, as compared to an atom with only two shells on the inside, the one with four shells would have a greater shielding effect and hence a greater radius because these electrons would not allow the nucleus to attract the outer electron towards itself. Hence, it would stay away from the nucleus, and hence the total radius from the nucleus to the outer electron would actually be greater. All right. So, in short, if the shielding effect is greater, the atomic radius would always be greater. Okay. The greater the shielding effect, the greater would be the radius. Now, let's look at the explanation of the group trend. Down the group, the number of shells they increase, right? Because going down the group, it is a fact that the number of protons are increasing. So you need more shells to accommodate them. So the shielding effect also increases because I told you that shielding effect actually depends upon the number of shells. If the shielding effect increases, then both the atomic as well as the ionic radius would increase down the group. This is a group trend. This is how it looks like. You can see how the ionic or the atomic radius is actually increasing. You can see the size is gradually increasing down the group. Let's move on to the period trend. Now, across the period, there is just a very unusual trend that is observed, and that is decrease in the size of the atoms. And let's just look at it and let's see what are the reasons. And the reasons that I've listed down over here are for 3 marks. Remember that, and they have been tested multiple times, so you make sure you learn them properly. Now, across the period, the number of shells they remain constant. Because remember, the period number actually tells you the number of the outer shell, right? So if you are in, for example, period 3, then that means all the atoms in that same period will have an outer shell that is the third shell, right? All of them would have the same third shell, right? So this means the number of shells are not changing at all as you go across the period. If the number of shells are not changing, will there be any impact on the shielding effect? No, not at all. If the number of shells are constant, the shielding effect is also constant. It's constant because the shielding effect, it depends upon the number of shells. So if the number of shells are constant, then shielding effect also remains constant. If the shielding effect remains constant, what about the nuclear attraction? Going across the period, the proton number is still increasing, right? If you're having more and more protons across the period, then that means the ability or the nuclear charge is actually increasing as well. And so the ability of the nucleus to attract the outer shell electrons is also increasing. So nuclear attraction increases due to more and more protons as you go across the period because the proton number is increasing. So you have an increasing, a strengthening nucleus with weaker defenses. With constant defenses, the defenses are not becoming stronger as you go across the period, but the nucleus is becoming stronger and stronger. As a result of this, the outer electron experiences a progressively stronger attraction on it. All right, and that stronger attraction tends to pull the electrons inward. So electrons are attracted more tightly to the nucleus as you go across the period, and hence the atomic radius decreases across the period. Just look at this trend right over here from sodium to chlorine. This is the same period 3, and as we go across the period, the atomic radius shrinks like this. All right. Now someone might ask, why is argon missing here? Argon is missing because argon is a noble gas, and its radius, the technique by which the radius of argon is measured is different from the technique by which these radii are measured. The radius of these normal elements other than the noble gases is called an atomic radius. But for noble gases, it's called van der Waal radius, and there's a entirely different technique to measure that, right? Because there's a van der Waal radius over there, and there's a different type of radius to measure it, to measure that radius. That radius does not follow the trend and is an exception to the trend. All right, and the radius actually becomes bigger all of a sudden after chlorine, and that is because the technique to measure that radius is different. All right, hence it's called a van der Waal radius. And this finishes off the discussion. All right, this finishes off this lesson. So if you guys have not subscribed yet, please make sure to subscribe. And you guys can follow us on our social media handles as well. Thank you so much.